Hi, Year 10. This beautiful sunny weather continues. What we did last lesson is we looked at a terminal velocity and looked at a velocity time graph for a skydiver. So like I've been doing, what I'd like you to do is a little start of this lesson, doing the back of your book, piece of paper, whatever it is I'd like you to sketch down now, again, I call it velocity, or you can call it speed. On the y-axis, time is going to be on the x-axis. And what I want you to do is sketch down a velocity time graph for a skydiver jumping out of a plane. Very exciting stuff. So I'd like you to stop this video, get a piece of paper out and sketch it out, and let's see what you've got. Okay, now welcome back. Hopefully you've got your little sketch in front of you. Did you get it correct or not? This is what we looked at last lesson. So what I've got my little sketch here I got speed, here I got time, and the graph looks like this, and it curves around to there. And just another picture I thought I'd share it with you. Here you've got unbalanced forces. The skydiver gets faster and faster and faster. But as they get faster and faster, the weight is always staying the same, like we looked last lesson, but the air resistance starts to increase. So as the air resistance starts to increase, the steepness or the acceleration gets less and less and less. Eventually here we got something where you have the air resistance acting up and the weight acting down. And basically now you're going to have balanced forces, so you reach terminal velocity. I hope you got that correct. So moving on to the second lesson is Newton's laws. You'll be doing it already, but this is a bit of recap and take things a little bit further. We're going to basically, this lesson is all about Newton's first law and state what it is, and also looking at what this thing is called inertia. Now, to help you with inertia, there's a famous trick you can do, and don't do this at home, please, unless you get permission from your parents, is where you can get a tablecloth and you can basically put crockery, cups, plates, whatever it is, on the tablecloth, and if you pull the cloth off quickly enough in the right way, everything stays there. Now, to show this in action, I'm going to go to a famous Stevie Spangler video, if I can get him working. Oh, no, I've got to have a Stevie Spangler video. I think he's over here. Here he is. Okay, and this is the table trick, and I'll quickly show you this video.
All right, so the first thing, we're going to whip the tablecloth off, because every kid that's out there that's watching, and I know you are, and you're saying, I got to whip the tablecloth off because you've always wanted to. Here's the secret. The first thing is you need to go get fabric that does not have a hem. So if you see that right there, see how there's not a hem?
That little
right?
sewn edge
so that little frayed thing that's right there, that's perfectly fine. That's what we want.
That thread I just pulled up, is that going to be a problem?
No, that's going to be fine. Okay. The second thing is this, is you're going to pull straight down to your toes. So on the side here, what it's going to look like is this, is you're going to hang on to it like this, and your hands are going to be here, and you're going to pull straight down like that.
Ooh,
hear that little whip?
Yeah, hear the whip.
That's good.
That's the sound of success.
That's good. That is the sound of success. All right. So fire it up. Let me just hear a little whipping action.
Right,
we'll just see how good it is.
Look what I've done.
It's perfectly fine. Yeah, you're going to be great. Okay. So hands there, whip down, ready, set, nice. Now, second rule is this: you never use your own. Now you're not done yet. Get it back going. All right. None of the elbow thing just yet, because you're not there.
All right. Okay.
All right. So now you never use your own dishes, right? You always use a friend's dishes. That's exactly right. All right. So here's what's going to happen. Let me put these together for you here like this. All right. So now it's the law of inertia, the tendency of an object to stay at rest until a force acts upon it. So gravity's pulling down this smooth cloth here, and the lack of an edge. Hopefully, it'll keep it in place. Ready? All right. So be a rock star. Grab the ends.
Me?
Do you think I'm doing it? All right. All right. Straight down. Ready? 3, 2, 1. Straight down. That was nice.
Thank you.
See, that was nice.
Thank you.
But see, most first graders can do that. So here, do that again. All right. So put it back up again, because I have another one for you that I thought might be kind of fun.
All right.
All right. So here's what happens: is you got it there. Yes, this is perfect. All right. So here we go. If we add mass, then that's probably a pretty good thing. So that's where these glasses going to come into play. So if you've ever seen somebody do it before, they sometimes will add something on top like this. Got that? And then we add a little bit of mass. All right. So here we go. So here's a little bit of mass. So how about a little bit here?
All evening.
You're going to be, and I think you're going to be good. Yeah, you're going to be just perfect at this. Isn't that great? Now, for a mere mortal, this would be good, but you are more than a mere mortal. So that's where this goes on top, and this
is
guy
not recommended.
is right up here like this. all right?
There's no way.
There's a strong possibility that this is not going to work, all right? But it's okay. We got to see your first one, and we'll cut all the rest out, all right?
Oh, gee.
Are you ready for this?
Is it me?
Yeah. Yeah, again, it's not me, all right? All right, so I'm going to move you down just a little tiny bit. I think you're going to be great.
Set me
right?
up for success
So you're going to be here like this, and your hands are tight, straight down to your toes.
Okay.
Got it? Straight down to your toes. No hesitation at all.
All right, okay.
All right,
Miss
ready?
Christensen is
Little
ready to
drum
exit
roll.
the studio.
I'm gonna count you in. Ready? 3, 2, 1, hard. And the crowd goes wild.
Thank you.
Now you can do your little thing here. Do your little thing here. Yes, that's perfect.
Okay.
Do you ever wish you...
That is a classic Stevie Spangler video. Americans can tell. And it's really tying back, want to show you is what is meant by this thing called inertia. Now, inertia is all related to the mass. And simply as the mass of the object increases, its inertia is going to increase. And what it means is a reluctance of things to change its speed or velocity. In other words, something will stay at rest unless a force acts on it. But if it's got a higher mass, it's got more inertia, therefore it's more likely to stay where it is. And that's why you actually be able to do this. If you put more and more, like you did at the end, glass tops full of water, you're going to increase the mass to actually make it move. And you think about, we've got a lorry picking off, start to accelerate. A lorry's got enormous amount more inertia, therefore it has even more reluctance to start to move. And that's where this thing inertia comes in. I think that video shows you very, very nicely it working in action. And it's also tied into Newton's first law. So in Newton's first law, this is a picture out of your book. And we have been looking at this already because we're looking at the terminal velocity, but I'm recapping on it. So here you've got a average student. Yes, looks like Harry to me. Does it? Anyway, you've got your average students, and here they are. They have got a weight of 750 newtons acting down. And then also what you've got is an other weight, a reaction force acting upwards, which is also going to be 750 newtons. Now, these two forces are balanced. Therefore, isn't the overall force going to be 0 newtons? Therefore, it is going absolutely nowhere. Again, you can have a car going here. Car going forward, here's your forward force. It could be 300 newtons. And then you got your air resistance, also 300 newtons. Again, the two forces are equal. Therefore, your resultant force is 0 newtons, balanced forces. But this car was already moving at, say, at 30 miles per hour. It will keep going at 30 miles per hour. Its speed will not change because the forces are balanced. Now, if you're a sad person like me at the weekends looking at the fact of the SpaceX taking the 2 American astronauts up to the International Space Station, that was a classic example of physics in action. When you had the Dragon capsule going around orbiting the Earth, if you have got it going stationary or at a constant speed, here you've got it stationary, no force acting it. In other words, if you've got no forces acting whatsoever, or you've got balanced forces, it will stay where it is. But in cases of orbiting the Earth at a steady speed, and this could be really, really shifting, could be example, be 1,000 miles per hour. And this is an amazing thing, we actually docked the International Space Station, it was moving, and the International Space Station moving. Here, you've got a steady speed, therefore its speed is not changing, therefore you have got no forces acting on it. And this happens in space because you've got no air resistance, and the only way you can make its speed change if you make the force unbalanced by, in fact, switching on the rockets like that. Okay? Now, to help you with this, and this is where I've got this little simulation and try and get onto it, is here you've got a mountain biker going along the ground. Now, in this case here, going back to what we looked before, and this again goes terminal velocity, but it's not a skydiver. Now, if I start this off, first we can see here, I've got a forward force of 350 newtons. I've got air resistance 146. Here, it's about 200, well, it's about 204 exactly, is going to be a resultant force. Therefore, because the forces are unbalanced, the speed is going to change. Hence, the velocity starting to increase. And like you've seen before in the videos I showed you beforehand on terminal velocity, slowly but surely get faster and faster. Your air resistance is going to start to increase. And now it has gone to, if I freeze my video, where we got 350, 350. The forces are balanced, therefore you reach terminal velocity. Now, what I'm going to do now, though, is suddenly increase the slope like this and watch what happens. Now, can you see the speed start to decrease? And the reason why the speed starts to increase is now the forward force is going to be 172. That's because you're going suddenly up a slope. You're trying to make it higher. Now it's not staying flat. Therefore, you've got an unbalanced force. And because you've got an unbalanced force, the speed starts to decrease. But eventually, as you go along like this, here now, the 172 will start to equal the 172 acting down. Now you've got balanced forces, and again, you reach your new terminal velocity. As another way a terminal velocity can happen, not only in skydivers, it also can happen in slopes. So, what I've done for you here is I'll quickly recap Newton's first law, which is going to be in your book, and it simply states this. If the forces are balanced, then there is no change in the way the object is moving. In other words, the speed is going to remain constant. If your forces are unbalanced, the object is going to speed up or slow down. It's going to get faster, it's going to decrease. In other words, you're going to have something called acceleration. And that is Newton's first law. So we'll move on to Newton's second law next lesson. Hope you enjoyed the video. Bye for now.